Good morning, everyone. This is Anandi Thakre from Section A3, Computer Science Engineering, roll number 50. My today's topic for quantum TA2 is Deutsch's algorithm, which is proposed by David Deutsch in 1985. It is a foundational quantum algorithm that demonstrates a potential speed up over classical algorithms for a specific problem. It addresses the task of determining whether a given function, which takes a single bit as input and produces a single bit as output, is either constant or balanced. There are two types of functions. First is constant function and the other is balanced function. The function always produces the same output, either 0 or 1, regardless of the input, can be termed as constant function, whereas the function produces different outputs for the two possible inputs. One input yields 0 and the other yield 1 is termed as balanced function. Classically, to determine if such a function is constant or balanced, one would need to evaluate the function twice. Once for input 0 and once for input 1, and then compare the results. Deutsch's algorithm, however, leverages the quantum principles like superposition and interference to achieve this determination with only one evaluation of the function using quantum oracle. The Deutsch algorithm relies on several fundamental quantum mechanics concepts and techniques to achieve its speed up over classical computation. First is qubits. The algorithm uses qubits, which are basic units of quantum information. Unlike classical bits, which must be 0 or 1, a qubit can exist in a superposition of both states simultaneously. Second is superposition. This principle allows the quantum computer to evaluate the function for all possible inputs in a single step, a process known as quantum parallelism. This is achieved by applying Hadamard gates to the input qubits at the beginning of the circuit. Third is quantum gates. Specific unitary transformations such as the Hadamard gate are used to manipulate the qubits states. These gates perform operations on quantum states in a reversible manner. Fourth, quantum oracle. The unknown function f of x is termed as a black box or oracle that performs a specific unitary transformation. The algorithm relies on the ability to implement this function as a quantum operation without reading to know its internal workings. Inference. This is the key mechanism that allows the algorithm to extract a global property from the superposition of function evaluations. Hadamard gates at the end of the circuit cause different computational paths to interfere constructively and destructively, amplifying the desired circuit. For the given problem, the function f of x, which is in a set from 0 to 1, goes from 0 to 1. This means that we are studying a function that takes an input of either 0 or 1 and outputs either 0 and 1. This explains that the function can be either constant, which is f of 0 is equals to f of 1. The function gives the same output for both inputs. And the next one can be balanced, which means f of 0 is not equals to f of 1. The function gives different outputs for 0 and 1. Classical computing requires two evaluations to know whether the function is constant or balanced, whereas the Deutsch algorithm requires only one evaluation. The following are the algorithm steps for solving the given problem. First is start with cat 0, cat 1. The algorithm begins with two qubits. The first qubit is the state 0 and the second qubit is the state 1. Second, apply Hadamard gate to both qubits. A Hadamard gate creates a superposition. Applying it to both qubits prepares them so that they can explore multiple possibilities at once. Third, Oracle UF interacts with the qubits. The oracle in the black box function that represents the unknown function f. It changes the qubits in a way that depends on whether f is constant or balanced. Fourth, apply Hadamard gate to the first qubit. Another Hadamard gate is applied, but only to the first qubit. This step helps extract the answer from interference patterns. Fifth, Measure the first qubit. Result. Finally, the first qubit is measured. If the result is 0, the function is constant, and if the result is 1, the function is balanced. The following problem shown on the screen has a circuit diagram where H means Hadamard gate. The given slide explains visual understanding. The main points can be termed as simultaneous input checking. The algorithm can process both inputs, f of 0 and f of 1 at the same time. Quantum superposition. This simultaneous evaluation is made possible by the principle of quantum superposition, which allows a quantum system to be in a multiple states at once. Quantum speedup. This ability to check multiple inputs concurrently is highlighted as the starting point for quantum speed advantages over classical computers. Our next question arises as what is an oracle? An oracle is a black box function embedded in a quantum gate that flips the phase depending on the function output, which allows the final measurement to reveal the answer. An oracle in the context of quantum computing, likely related to the Deutsch algorithm mentioned in the presentation, is described as a black box function that is integrated into a quantum gate. It modifies the phase of the quantum state based on the result of the function it represents. The specific phase manipulation is the key mechanism that enables the final measurement of the quantum system to provide the desired answer or solution. A real-world relevance of Deutsch algorithm as presented in the slide lies in its educational value as a foundational example in quantum computing. Even though it solves a relatively simple problem, it teaches several key concepts. Quantum circuit design provides a basic framework for how to structure quantum gates and operations to perform a specific task. Building blocks of quantum algorithms demonstrates the core principles that are used in more advanced and powerful quantum algorithms. Understanding superposition and interference illustrates how quantum mechanics principles such as qubit existing in multiple states at once and manipulating quantum amplitudes can be leveraged for computation. The Deutsch algorithm holds significance important in quantum computing for several key reasons. First, demonstration of quantum advantage. It is the first algorithm to show that quantum computer could potentially solve a problem faster than any classical computer. Basis for Deutsch-Jozsa algorithm. It serves as a foundational concept for the Deutsch-Jozsa algorithm, which further explores the potential for quantum speedup on a specific problem. Helps understanding quantum parallelism. The algorithm effectively demonstrates the concept of quantum parallelism, where a quantum computer evaluates a function for multiple inputs simultaneously. Introduces inference core of quantum computing. It highlights the use of quantum inference, a crucial principle in quantum mechanics used to amplify the correct results and cancel out the incorrect ones in quantum computations. Finally, coming to the conclusion of this PowerPoint presentation. The Deutsch algorithm in quantum computing has various conclusions. First of it can be termed as algorithm's power. The Deutsch algorithm demonstrates the ability of quantum computing to to outperform classical approaches. Educational values. It is considered an ideal introductory algorithm for students learning about quantum computing principles. Thank you. This is Anandi Thakre from Section A3 Computer Science Engineering, roll number 50.